There's a star out there so massive that if you placed it where our sun sits, it would swallow everything. Mercury, Venus, Earth, Mars, gone. Jupiter, consumed. Saturn's rings, obliterated. The surface of this stellar monster would stretch somewhere between Jupiter and Saturn's orbit, turning our entire inner solar system into nothing more than a memory inside a ball of superheated gas. This isn't science fiction. This is Stephenson 218, and it currently holds the title as the largest known star in the observable universe. But here's what makes this discovery truly unsettling. We almost missed it entirely. 20,000 light-years away, hidden in the constellation Scutum, this red hypergiant went unnoticed for decades, despite being over 2,000 times wider than the Sun. The reason? It's wrapped in layers of dust and gas so thick that visible light barely escapes. Only when astronomers pointed infrared telescopes at a specific cluster of stars did they realize something absolutely enormous was lurking there, pulsating with a luminosity that dwarfs anything in our stellar neighborhood. You're probably wondering how something that massive can even exist. Stars aren't supposed to get that big. There are theoretical limits, mathematical boundaries that should prevent stellar bodies from inflating beyond certain points. Physics itself seems to argue against the existence of Stephenson 2-18. Yet there it is, defying our models, challenging our understanding of how stars work, and forcing astronomers to reconsider what they thought they knew about the upper limits of stellar evolution. The numbers are difficult to process. Stephenson 2-18 has a radius approximately 2,150 times that of our Sun. Let that sink in for a moment. If the Sun were the size of a basketball, Stephenson 2-18 would tower over 20 stories high. The volume comparison is even more staggering. You could fit roughly 10 billion suns inside this single star. 10 billion. But size isn't the only remarkable characteristic. This stellar giant shines with the power of 436,516 suns combined, pumping out energy at a rate that seems almost wasteful. All that power radiates from a surface that's surprisingly cool for a star. Only about 3,200 Kelvin. That's roughly half the temperature of our Sun's surface, which explains why Stephenson 2-18 glows with that characteristic deep red color, rather than the yellow-white we're accustomed to seeing in our sky. The discovery story itself reads like a detective novel. American astronomer Charles Bruce Stephenson was conducting a deep infrared survey when he stumbled upon an unusual cluster of red supergiants. The cluster, eventually named Stephenson 2, contained multiple massive stars, but one particular object kept showing up in the data with peculiar characteristics. Initially labeled as star number 1, it was later reassigned the number 18 when astronomers realized it belonged to an outlying group within the cluster. The multiple naming conventions, Stephenson 2-18, ST 2-18, Stephenson 2DFK1, reflect how our understanding of this object evolved over time. What astronomers found particularly intriguing was the infrared excess. This star was pumping out far more infrared radiation than expected, suggesting something unusual was happening in its outer layers. The thick cocoon of dust surrounding Stephenson 2-18 wasn't just obscuring the star, it was telling a story about violent mass loss, unstable outer layers, and a stellar object in the final throes of its existence. The cluster itself is relatively young, only about 17 million years old, give or take 3 million years. In cosmic terms, that's practically infantile. Our Sun, by comparison, has been burning for 4.6 billion years and still has billions more to go. But massive stars like Stephenson 218 live fast and die young, burning through their nuclear fuel at prodigious rates. Despite being millions of times more massive than Earth, this star likely has only a few million years left before it ends its life in a spectacular supernova explosion. Mass loss is one of the defining characteristics of these red hypergiants. Stephenson 2-18 is shedding material at approximately 1.35 times 10 to the power of -5 solar masses per year. That might sound insignificant, but it means this star is losing mass equivalent to Earth's weight roughly every 3 years. This material doesn't just disappear, it forms an expanding shell of gas and dust around the star, creating the infrared signature that helped astronomers identify it in the first place. Massive emissions from the star provide additional clues about what's happening in its outer atmosphere. These naturally occurring microwave lasers are created when molecules in the stellar wind, water vapor, silicon monoxide, and others, are energized by the star's radiation. The presence of these masses indicates extreme conditions in the surrounding environment, with temperatures, densities, and radiation levels that would be instantly fatal to anything we could possibly imagine sending there. For years, a different star held the title of largest known. Scutum, discovered back in 1860 by German astronomers at the Bonn Observatory, was long considered the champion. Early measurements suggested a radius around 1,700 times that of the Sun, which would make it large enough to contain nearly 5 billion solar volumes. That's the kind of scale that breaks our ability to conceptualize size. We simply don't have reference points for objects that enormous. But astronomical measurements are tricky, especially when dealing with objects thousands of light years away. Distance uncertainties translate directly into size uncertainties. If you're wrong about how far away something is, you'll be wrong about how big it is. The parallax method, measuring how much a star appears to shift against the background as Earth orbits the Sun, provides the most reliable distance measurements, but it requires extraordinary precision for objects at stellar distances. When the European Space Agency's Gaia spacecraft began releasing its precision astrometry data, astronomers rushed to recalculate the distances to many famous stars. The results were shocking. Scutum, it turned out, was significantly closer than previously thought. About 5,871 light-years away, rather than the earlier estimates that placed it beyond 9,000 light-years. Closer distance means smaller size. The revised radius dropped to roughly 909 solar radii, still enormous by any standard, but nowhere near the record-breaking measurements that had made Scutum famous. This is where the story gets messy, because astronomy isn't as clean and definitive as we'd like it to be. Different measurement techniques yield different results. Infrared observations give one answer, optical measurements give another, and theoretical models based on luminosity and temperature give yet another. The uncertainties can be massive, sometimes 50% or more. That margin of error means the largest star title keeps changing hands as new data comes in and old measurements get revised. Several other contenders vie for the crown. NML Cygni, heavily obscured by dust in the constellation Cygnus, has radius estimates ranging from 1,183 to 2,770 solar radii, depending on which study you trust. VY Canis Majoris, perhaps the most famous red hypergiant, has been described as everything from 1,420 to over 1,900 solar radii in various papers. WOHG 64, located in the Large Magellanic Cloud outside our galaxy, presents its own measurement challenges due to its extreme distance. The problem is fundamental. These stars are surrounded by thick shells of gas and dust that make it difficult to determine where the star ends and the surrounding material begins. Unlike our Sun, which has a relatively well-defined surface, red hypergiants have extended, tenuous outer layers that gradually fade into the surrounding space. Defining the radius becomes more of a philosophical question than a straightforward measurement. What we do know with certainty is that all of these objects represent the extreme upper end of stellar size. They're red supergiants or hypergiants, stars with spectral types K or M, indicating surface temperatures below 4,100 Kelvin. They're in the final stages of their lives, having exhausted the hydrogen in their cores and moved on to fusing heavier elements. The fusion of these heavier elements produces less energy per unit mass, which means the star must expand dramatically to maintain the pressure needed to support its outer layers against gravitational collapse. This expansion is what creates these stellar monsters. A star that began its life perhaps 25 to 40 times the mass of our Sun swells to dimensions that seem physically impossible. The outer layers become so extended that their density drops to less than Earth's atmosphere at sea level. In some regions, the density might be closer to what we'd consider a laboratory vacuum. You could, in theory, fly a spacecraft through the outer layers of these stars without immediately vaporizing, though the radiation would still kill you pretty quickly. The ballooning effect creates another counterintuitive situation. These massive stars aren't particularly heavy for their size. UY Scuti, despite being able to contain 5 billion suns by volume, probably masses only 25 to 40 times what our Sun does. The vast majority of its volume is extremely low-density gas. Stephenson 2-18 is likely similar, though precise mass estimates remain uncertain. Size and mass don't scale linearly in the stellar world, especially for these dying giants. Temperature is another surprise. You might expect the largest stars to be the hottest, but the opposite is true. Our Sun's surface sits at about 5,500 Kelvin, while Stephenson 2-18 manages only 3,200 Kelvin. This cooler temperature is precisely why these stars glow red rather than the yellow or blue-white of hotter stars. The relationship between temperature, size, and luminosity follows from the Stefan-Boltzmann law. A star's total energy output depends on both its temperature and its surface area. These giants compensate for their low temperatures with absolutely enormous surface areas, allowing them to shine with the power of hundreds of thousands of suns, despite being relatively cool. The hunt for the largest star continues, with new candidates emerging as telescope technology improves. Infrared surveys are particularly important because they can penetrate the dust that obscures these objects in visible light. The James Webb Space Telescope, with its powerful infrared capabilities, may revolutionize our understanding of these stellar giants by providing clearer views of their surfaces and surrounding environments. What drives astronomers to pursue these measurements with such dedication? Beyond the simple human fascination with extremes, the biggest, the brightest, the most distant, these stars tell us something fundamental about the laws of physics. They're natural laboratories where matter behaves under conditions we can never reproduce on Earth. The processes happening inside Stephenson 218 right now are forging elements that will eventually seed the next generation of stars and planets. The iron in your blood, the calcium in your bones, the oxygen you're breathing, all of it was created inside stars like this one. Understanding how stars reach these extreme sizes helps us understand stellar evolution more broadly. Why do some stars become red supergiants while others end their lives differently? What determines the maximum possible size for a star? Are there physical limits we haven't discovered yet? Each new measurement, each refined distance estimate, each improved model brings us closer to answering these questions. The current record holder, Stephenson 218, represents our best answer to the question of stellar size limits based on available evidence. But that answer comes with significant error bars and multiple caveats. The measurement uncertainties are large enough that tomorrow's data might crown a different champion. NML Cygni could reclaim the title if its distance proves to be at the farther end of current estimates. A completely unknown star might be discovered in some dusty corner of the galaxy, dwarfing everything we've found so far. What seems certain is that we're approaching theoretical limits. Stars can't grow arbitrarily large. Physics won't allow it. The balance between gravitational collapse and radiation pressure has boundaries. Cross those boundaries and the star becomes unstable, shedding its outer layers in violent eruptions or potentially disrupting entirely. The very largest stars we observe may be teetering right at that edge, held together by the thinnest margin of stability. These stellar behemoths won't last forever. In fact, they won't last long at all by cosmic standards. The same processes that allow them to grow so large, the fusion of progressively heavier elements in their cores, are rapidly depleting their fuel reserves. What happens when that fuel runs out? The answer involves some of the most violent and energetic events in the universe, explosions that briefly outshine entire galaxies and forge elements that can't be created any other way. The final moments of these giants make their brief lives seem almost anticlimactic by comparison. When a red supergiant exhausts its nuclear fuel, its core collapses in milliseconds, triggering a supernova explosion so powerful it releases more energy in seconds than our sun will produce in its entire 10 billion year lifetime. The shockwave tears through the star's outer layers, accelerating material to a significant fraction of light speed and heating it to billions of degrees. For a few weeks, a single dying star can outshine the combined light of hundreds of billions of normal stars. But there's something stranger happening with the largest red supergiants. They don't always go quietly. VY Canis Majoris have been shedding mass at an extraordinary rate, losing material equivalent to Earth's mass every 6 years. Recent Hubble observations revealed massive arcs and knots of ejected material surrounding the star, some as large as our entire solar system. These aren't gentle stellar winds, they're violent eruptions, hurling chunks of the star's outer layers into space at speeds of hundreds of kilometers per second. Why does this matter? Because it suggests these extreme supergiants might destroy themselves before they even reach the supernova stage. Imagine a star so massive, so luminous, that its own radiation pressure becomes strong enough to blow itself apart. The photons streaming outward from the core push harder than gravity can pull inward. Material at the surface becomes unbound, lifted away from the star in massive eruptions. Over time, the star sheds so much mass that its core might no longer be heavy enough to trigger a supernova when fusion finally stops. This process, called superwind mass loss, could explain why we don't observe supergiants much larger than Stephenson 2-18. There might be a natural ceiling to stellar size, not because stars can't grow larger, but because once they do, they immediately begin tearing themselves apart. The timeline gets interesting here. These stars are young, only 10 to 20 million years old. Our Sun, by comparison, has been burning steadily for 4.6 billion years and has another 5 billion to go. But a red supergiant's profligate energy output comes at a steep price. They burn through their fuel reserves thousands of times faster than smaller stars, racing through their entire life cycle, while smaller stars are still settling into middle age. Scutum will likely explode within the next few million years. Stephenson 218 might beat it to the finish line. Both could have already detonated, and we simply don't know yet because their light takes tens of thousands of years to reach us. Somewhere in our galaxy, a brilliant new star might already be shining in someone else's sky, marking the death of one of these behemoths, while we remain in darkness, waiting for the news to arrive. What triggers the final collapse? It's a story about nuclear fusion reaching its limits. A star like our Sun fuses hydrogen into helium in its core. That's it. That's the whole show for its entire main sequence lifetime. But massive stars don't stop there. When the hydrogen runs out, the core contracts and heats up until it's hot enough to fuse helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. Each stage produces less energy and burns faster than the last. Hydrogen fusion might last millions of years. Silicon fusion lasts about a day. The core of a dying red supergiant resembles an onion, with shells of different elements fusing at different depths. Hydrogen burns in the outermost shell, helium underneath that, then carbon, neon, oxygen, silicon. Each layer progressively hotter and denser as you approach the center. At the very core sits iron, the end of the line. Fusing iron doesn't release energy, it consumes energy. When the core turns to iron, the star's power source shuts off completely. What happens next occurs faster than you can blink. Without fusion to support it, the iron core collapses. In less than a second, a ball of iron the size of Earth compresses down to a sphere maybe 20 kilometers across. The density becomes so extreme that protons and electrons merge into neutrons, releasing a flood of neutrinos that carry away most of the explosion's energy. The outer layers, falling inward at nearly a quarter the speed of light, hit the rigid neutron core and bounce. That bounce generates the shock wave that tears the star apart. The supernova itself is just the visible afterglow of this catastrophic core collapse, the dying gasp of a star that once dominated its region of space. For Stephenson 2-18, the explosion will be spectacular beyond imagining. If you were observing from a safe distance, say a few hundred light years away, the supernova would appear in our sky as bright as the full moon, despite being 20,000 light years distant. It would be visible in broad daylight for weeks. The expanding debris shell would glow for months, gradually fading as it cooled and dispersed into the interstellar medium. But here's what really matters. That debris contains all the elements forged during the star's life and in its final explosive moments. Carbon, oxygen, nitrogen, silicon, calcium, iron, elements that didn't exist in appreciable quantities when the universe began. The first stars were made only of hydrogen and helium. Everything heavier comes from stellar nucleosynthesis and supernova explosions. The atoms making up your body were created inside stars like Stephenson 218. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all forged in stellar cores and scattered by supernova explosions billions of years ago. You are, quite literally, made of stardust from dead stars. This cosmic recycling continues today. The material ejected by dying supergiants doesn't just drift away into nothingness. It forms vast clouds of gas and dust that eventually collapse under their own gravity to form new stars and planets. The next generation inherits the chemical legacy of the previous one, starting with a richer mix of elements that makes complex chemistry and eventually life possible. Some supergiants might not even explode as standard supernovae. The very most massive could collapse directly into black holes, their cores so heavy that nothing can stop the gravitational collapse. The outer layers fall inward and disappear beyond the event horizon, taking their elements with them. These failed supernovae leave behind black holes and little else, recycling almost nothing back into the cosmos. Others might become hypernovae, explosions even more energetic than regular supernovae, possibly accompanied by gamma-ray bursts that could sterilize planets dozens of light years away. The fate depends on the star's mass, rotation rate, and magnetic field strength, factors we're still struggling to measure accurately for these distant giants. The uncertainty extends to their remnants. A typical red supergiant leaves behind a neutron star, an object so dense that a teaspoon of its material would weigh as much as Mount Everest. These neutron stars spin rapidly, sometimes hundreds of times per second, emitting beams of radiation that sweep across space like cosmic lighthouses. We detect them as pulsars, precise cosmic clocks that helped astronomers discover the first planets outside our solar system. But the largest supergiants might skip the neutron star phase entirely, collapsing straight into black holes. Stephenson 218's core could already be massive enough that no amount of neutron degeneracy pressure can prevent total collapse. When it finally detonates, the core might disappear into a black hole while the outer layers are still falling inward. These stellar mass black holes themselves have interesting fates. They don't just sit there. They can merge with other black holes in violent collisions that shake the fabric of space-time itself, sending gravitational waves rippling across the universe. LIGO and other gravitational wave detectors have now observed dozens of these mergers, each one representing the final chapter in the lives of massive stars that died long ago. The existence of stars like Stephenson 218 pushes against theoretical boundaries in other ways too. How did they form in the first place? Standard star formation theory suggests that radiation pressure should prevent clouds of gas from collapsing into such massive objects. The forming star's own light should blow away the infalling material before it can accumulate. Yet clearly, these monsters exist, meaning something about our formation models remains incomplete. One possibility involves runaway mergers in dense star clusters. Perhaps Stephenson 218 didn't form as a single massive star, but grew by swallowing smaller companions in a gravitationally crowded environment. The Stephenson 2 cluster contains multiple red supergiants, in a relatively small region of space, suggesting conditions that favor the formation or evolution of extremely massive stars. Another factor might be metallicity, the abundance of elements heavier than helium. Stars in our galaxy today form from gas enriched by previous generations of supernovae. This enriched gas cools more efficiently, potentially allowing larger clouds to collapse and form more massive stars. The early universe, with its purely hydrogen and helium composition, might not have produced red supergiants like we see today. These considerations matter for understanding how galaxies evolve. Massive stars, despite their rarity, have outsized influence on their surroundings. Their intense radiation ionizes huge volumes of gas, creating glowing nebulae visible across cosmic distances. Their stellar winds and eventual supernova inject enormous amounts of energy into the interstellar medium, triggering new waves of star formation, while simultaneously blowing gas out of smaller galaxies entirely. The largest stars also serve as probes of stellar physics in extreme regimes. They test our understanding of how matter behaves at temperatures of millions of degrees, how radiation pressure affects stellar structure, how magnetic fields interact with convection in stellar atmospheres. Every measurement we make, every spectrum we analyze, every distance we refine adds another data point to help constrain our models. Which brings us back to the measurement challenges. Why is it so difficult to pin down the sizes of these stars with precision? Distance is the primary culprit. If you're off by 20% in your distance estimate, you're off by 44% in your calculated radius. And measuring distances to objects 20,000 light-years away remains remarkably difficult. The Gaia spacecraft has revolutionized distance measurements for relatively nearby stars, but even Gaia struggles with objects as distant and obscured as Stephenson 218. Parallax measurements, the apparent shift in a star's position as Earth orbits the Sun, work brilliantly for nearby stars. For something 20,000 light-years distant, however, that angular shift becomes almost imperceptibly tiny. You're trying to measure an angle smaller than a millionth of a degree through layers of intervening dust and gas that scatter and absorb light unpredictably. The zone of avoidance, that band of sky where the Milky Way's disk blocks our view, makes this exponentially harder. Temperature measurements introduce another layer of uncertainty. We determine a star's temperature by analyzing its spectrum, the rainbow of wavelengths it emits. But massive cool stars have complex atmospheres with powerful stellar winds that distort these spectra. Molecules form in the cooler outer layers, creating absorption bands that complicate the analysis. Is that temperature reading representative of the photosphere, the visible surface? Or are we seeing light that's already been modified by dust and gas surrounding the star? Then there's the variability problem. Stephenson 218 isn't a steady, unchanging beacon. These red supergiants pulse and fluctuate, their surfaces rising and falling like slow-motion ocean waves. The radius you measure this year might differ from next year's measurement by hundreds of millions of kilometers. Which value represents the true size? Some astronomers argue we should report average radii, others prefer maximum extent. The choice fundamentally affects the rankings. See, infrared observations help cut through some of this confusion. Dust that blocks visible light proves transparent to longer infrared wavelengths, allowing us to peer through the obscuring material. The Very Large Telescope's interferometry work combined light from multiple telescopes to achieve resolution impossible with any single instrument. But even infrared observations require assumptions about dust composition, density, and distribution between us and the target star. Consider what happens when distance estimates change. Scutum demonstrated this dramatically. For years it held the record with a radius around 1,700 solar radii. Then Gaia's improved parallax measurements suggested it might be significantly closer than previously thought. Closer distance means lower luminosity. Lower luminosity at the same temperature means smaller radius. Suddenly, Scutum dropped to around 755 solar radii in some analyses, less than half its former size. Does this mean Scutum actually shrank? Obviously not. The star itself remained unchanged. What changed was our measurement precision and the models we use to interpret observations. This highlights something crucial about astronomical measurements. They're model-dependent. We can't put a tape measure across a star. We observe certain properties, brightness, spectrum, sometimes angular diameter, then use theoretical models to infer others like radius and luminosity. Different research teams might use slightly different model assumptions. One group might assume a certain chemical composition based on the star's location in the galaxy. Another might factor in rotation effects. A third might account for atmospheric convection differently. Each choice propagates through the calculations, producing somewhat different final estimates. The published error bars, those plus or minus values, attempt to capture this uncertainty, but they can't account for unknown systematic biases in the models themselves. Stephenson 218's extreme infrared excess suggests something unusual happening in its immediate environment. Perhaps it ejected a massive shell of material in a recent outburst. Perhaps its stellar wind varies dramatically in density and temperature. These circumstellar complications mean we're not just measuring the star itself, but the star plus its extended atmosphere and surrounding material. Where exactly does the star end and space begin? For a diffuse red supergiant, that boundary proves surprisingly ambiguous. The cluster environment adds context that helps constrain some uncertainties. If we know Stephenson 2-18 belongs to the same cluster as other red supergiants, we can assume they all lie at roughly the same distance. Their relative brightnesses then tell us about their relative luminosities. This doesn't eliminate distance uncertainty entirely, but it helps by providing multiple cross-checks. Astronomers call this technique main sequence fitting, comparing the cluster's stars to theoretical models of stellar evolution. Age estimates for the Stephenson 2 cluster, around 17 million years, provide another constraint. Stars of certain masses evolve at predictable rates. If the cluster is 17 million years old, the most massive stars still present must have formed with just the right initial mass to have survived this long without exploding. The red supergiants we see represent stars that began life with perhaps 25 to 40 solar masses, now nearing the ends of their brief, violent lives. Why do some massive stars become red supergiants, while others skip this phase? Rotation matters significantly. Rapidly rotating stars mix their interior material more thoroughly, bringing fresh hydrogen into the core and changing their evolutionary path. They might burn hotter and faster, never cooling enough to expand into red supergiant territory. Non-rotating or slowly rotating stars of similar mass follow different tracks through temperature-luminosity space. potentially spending significant time as cool, bloated giants. Metallicity plays a role too. Stars, rich in elements heavier than helium, lose mass more efficiently through stellar winds. Those winds, driven by radiation pressure on metal atoms in the atmosphere, can strip away the star's outer layers before it fully expands into the red supergiant phase. The Stephenson 2 cluster's location in the galactic plane suggests its stars formed from relatively metal-rich material, yet they clearly became massive red supergiants anyway. The details of how metallicity affects evolution at these extreme masses remain debated. Binary companions complicate matters further. Many massive stars have stellar partners orbiting nearby. These companions can exchange mass, merge, or tidally affect each other's evolution in ways that single star models don't capture. Could Stephenson 218 have grown by cannibalizing a companion? The cluster's density suggests close encounters between stars might occur relatively frequently. Such interactions could explain some of the more extreme properties we observe. Mass loss rates provide clues about these stars' futures. Stephenson 2-18 sheds roughly 0.0000135 solar masses annually, about 13 times Earth's mass every year. At this rate, it loses material equivalent to our entire Sun every 74,000 years. This isn't sustainable indefinitely. Eventually, the star will shed enough mass that its structure fundamentally changes. But when? And will it explode before or after crossing some critical threshold? The massive stellar wind doesn't just carry away mass. It carries angular momentum, slowing the star's rotation. It enriches the surrounding interstellar medium with heavy elements forged in the stellar interior. Nitrogen, carbon, oxygen, products of internal nuclear burning, stream outward at hundreds of kilometers per second. When this material collides with slower-moving gas previously ejected, shock waves heat the collision zone to millions of degrees, producing X-rays we can detect from Earth. These wind collision regions create complex nested shells of material around evolved massive stars. Hubble images of similar objects reveal intricate structures, loops, arcs, knots of denser gas. Each feature tells a story about past episodes of enhanced mass loss, about changes in wind velocity or direction, about the star's asymmetric pulsations. Stephenson 218, buried deep in dust, hasn't been imaged with this kind of detail yet. What would we see if we could? Dust formation in the stellar wind itself presents puzzles. How do solid grains condense from hot gas? What determines grain size and composition? Observations show that some red supergiants, VY Canis majoris for instance, produce enormous dust particles, practically boulders by interstellar standards. The dust around Stephenson 218 might be similarly unusual, contributing to its extreme infrared brightness. This dust eventually gets dispersed into space, providing raw material for future generations of stars and planets. Think about that for a moment. The carbon in your body, the oxygen you breathe, the iron in your blood, all forged inside stars. Much of it came from red supergiants not unlike Stephenson 2-18. These stellar giants are essentially massive element factories, transmuting hydrogen into everything up to iron through nuclear fusion, then distributing their products across the galaxy. When they finally explode, the supernova creates even heavier elements, gold, platinum, uranium, through rapid neutron capture in the explosion's maelstrom. Without red supergiants and their explosive deaths, the universe would remain mostly hydrogen and helium. No rocky planets, no chemistry, no life. The existence of stars like Stephenson 218, extreme as they are, represents an essential step in cosmic chemical evolution. Their brief lives and spectacular deaths seed the galaxy with the building blocks of complexity. This cosmic perspective makes the measurement uncertainties almost trivial. Whether Stephenson 218's radius is 2,150 or 2,000 or 1,800 solar radii doesn't change its fundamental nature or importance. It remains an extraordinary object pushing the boundaries of stellar physics, regardless of whether it precisely holds the size record. The quest to refine that number drives technological advancement and theoretical understanding that benefits all of astronomy. Future instruments promise better answers. The extremely large telescope, currently under construction in Chile, will dwarf even the very large telescope in light-gathering power and resolution. Space-based infrared observatories, free from atmospheric interference, will map these dust-shrouded giants with unprecedented clarity. Gravitational wave detectors might eventually catch the supernova itself whenever it occurs, providing data about the star's final moments and the black hole left behind. Until then, we work with what we have. Careful statistical analysis of existing data, cross-checks between different observational techniques, detailed comparison with theoretical models. Gradually, measurement by measurement, the picture sharpens. The error bars shrink, our confidence grows. But some uncertainty will always remain. That's the nature of astronomy at extreme distances. What we can say with confidence, Stephenson 2-18 ranks among the very largest stars ever discovered. It exemplifies the extreme endpoint of stellar evolution for massive stars. It will die spectacularly, probably within the next few 100,000 years, though that timeline remains uncertain. Its supernova will briefly outshine entire galaxies, visible across much of the universe. And the black hole it leaves behind will persist long after our sun has died, a permanent scar in space-time marking where one of the universe's largest stars once blazed. The neighborhood surrounding Stephenson 218 tells its own fascinating story. This star doesn't exist in isolation. It's part of a stellar cluster, a family of stars born from the same molecular cloud roughly 17 million years ago. Stellar clusters serve as cosmic laboratories. All members form simultaneously from the same material, which means differences between them reveal how stellar evolution depends on initial mass. Stephenson 2, the cluster containing our giant, hosts about 26 red supergiants, an extraordinary concentration of these rare objects. Why so many? The cluster's age provides the answer. 17 million years ago, a massive cloud of gas and dust collapsed under its own gravity, fragmenting into hundreds or thousands of protostars. The most massive among them evolved fastest. They've already burned through their hydrogen fuel, swelled into red supergiants, and now approach death. Lower mass stars in the same cluster remain on the main sequence, quietly fusing hydrogen with billions of years left to live. This concentration of red supergiants makes Stephenson 2 invaluable for research. Astronomers can study multiple examples of roughly the same evolutionary phase, all at the same distance, all with similar initial compositions. Differences between cluster members, variations in size, luminosity, mass loss rate, reveal how subtle factors influence late stellar evolution. Some cluster members might be slightly more massive than Stephenson 2-18, yet smaller. Others might be losing mass more rapidly, or possess different rotation rates, or have different initial chemical compositions. One cluster member might explode as a supernova next year. Another might persist for another 100,000 years. We can't predict individual fates with precision, but statistical analysis of the cluster population constrains theoretical models. How many red supergiants should exist for a cluster of this age and mass? How should their properties distribute? Theory and observation must match, or something's wrong with our understanding. The cluster itself sits embedded in the Scutum crux arm of the Milky Way, a spiral arm rich with star formation. Massive molecular clouds populate this region, birthing stellar clusters continuously. Many young clusters remain hidden behind dust, detectable only in infrared wavelengths. Stephenson 2 happens to be positioned where we can observe it despite the obscuration, but hundreds of similar clusters likely exist along that spiral arm, currently invisible to our telescopes. Consider the implications. If Stephenson 2 contains 26 red supergiants and similar clusters exist throughout the spiral arm, how many stars like Stephenson 2-18 populate the galaxy right now? Hundreds? Thousands? Each one representing a massive star in its final phase, each destined to explode within the next million years. The galaxy experiences perhaps one supernova per century on average. Most go undetected, obscured by dust or occurring on the galaxy's far side, but detection capabilities improve constantly. The next galactic supernova will be studied with instruments our predecessors couldn't imagine. Gravitational wave detectors might catch the collapse itself. Neutrino observatories will detect the burst hours before light emerges from the explosion. X-ray and gamma-ray satellites will track the fireball's expansion in real time. Optical telescopes will obtain spectra revealing the explosion's physics in unprecedented detail. When will Stephenson 2-18 explode? Impossible to say. These stars are fundamentally unstable. They lose mass episodically, experiencing eruptions and outbursts that temporarily alter their structure. Each major mass loss event changes the star's evolutionary trajectory slightly. Remove enough of the outer envelope, and the core might get exposed prematurely, triggering different physics than if the star had retained more mass. Some theoretical models suggest red hypergiants like this might skip the supernova phase entirely, instead collapsing directly into black holes with minimal visible fireworks. The core becomes so massive that when fusion ceases, collapse proceeds so rapidly that the outer layers can't follow. The star simply winks out, leaving a black hole behind. No explosion, no scattered elements, just sudden disappearance. Alternative scenarios exist. Maybe the star sheds enough mass that the remaining core, while still massive enough to form a black hole, undergoes a more conventional core collapse supernova first. Or perhaps mass loss removes so much material that only a neutron star forms instead of a black hole. These outcomes depend sensitively on the star's total mass, its rotation rate, and how much mass it loses during the red supergiant phase. Current observations suggest Stephenson 2-18 is shedding mass prodigiously, perhaps more than 10,000th of a solar mass per year. That sounds tiny until you calculate how much disappears over millennia. In just 10,000 years, the star might lose 1/10 of a solar mass or more. Over 100,000 years, a full solar mass could vanish. This mass loss rate, if sustained, significantly affects the star's ultimate fate. Where does all that mass go? Into space, forming an expanding nebula around the star. This circumstellar material eventually disperses into the interstellar medium, mixing with other gas and dust. Some will get incorporated into future generations of stars. Some might become part of planetary systems. The iron and silicon and carbon streaming away from Stephenson 218 right now could, billions of years hence, form worlds where life evolves. Tracking this mass loss directly remains extremely difficult. The dust obscures our view of the star itself, and the circumstellar environment is complex and dynamic. Observations at different wavelengths reveal different aspects. Infrared shows warm dust close to the star. Radio observations detect molecules farther out. Visible light scatters off dust grains, creating reflection nebulae. Piecing together a complete picture requires combining data from multiple observatories across the electromagnetic spectrum. Maser emission provides particularly useful diagnostics. Masers are the microwave equivalent of lasers, naturally occurring amplification of specific molecular transitions. Silicon monoxide and water molecules in the circumstellar envelope can produce intense Maser emission when conditions are right. These masses appear as bright spots in radio observations, and their velocities reveal how material flows away from the star. Stephenson 2-18 exhibits strong Maser emission, indicating dense molecular gas in its immediate vicinity. The Maser velocities suggest material accelerates as it moves outward, pushed by radiation pressure and possibly by shock waves propagating through the circumstellar envelope. This acceleration mechanism remains somewhat mysterious. Photons from the star strike dust grains, imparting momentum that pushes them outward. Gas molecules couple to the dust through collisions and drag along. But the details, grain sizes, gas-to-dust ratios, magnetic fields, turbulence, all affect how efficiently this process works. Theoretical models attempt to reproduce the observed Maser properties by simulating the circumstellar environment in detail. These simulations require massive computational resources. You're modeling a three-dimensional volume tens of astronomical units across, filled with gas and dust at varying densities and temperatures, all interacting through radiation, gravity, and hydrodynamics. The calculations can run for weeks on supercomputers, producing terabytes of data that must be analyzed and compared with observations. When models and observations match, confidence grows that we understand what's happening. When they don't match, something's wrong. Either the observations need refinement, or the models require adjustment, or both. This iterative process gradually improves our understanding. Each new observation constrains the models further. Each refined model suggests new observations to make. The broader context matters too. Stephenson 218 doesn't exist in a vacuum. It's part of a galactic ecosystem where stars, gas, and dust interact continuously. The mass this star sheds enriches the interstellar medium with heavy elements. Other stars incorporate that enriched material. Supernova shockwaves from previous generations compress interstellar gas, triggering new star formation. Stellar winds from massive stars carve bubbles and cavities in molecular clouds. This cycle of stellar birth, life, and death has operated for billions of years, gradually increasing the galaxy's heavy element content. Early in the galaxy's history, only hydrogen and helium existed. First-generation stars formed from pristine primordial gas, lived brief lives, and exploded, releasing the first heavy elements. Second-generation stars incorporated those elements, produced more, and exploded in turn. Generation after generation, the metallicity increased. Our Sun is perhaps a 100th generation star, containing elements forged in dozens of previous stellar generations. The Earth formed from material that had cycled through multiple stars. Your body contains atoms created in stellar cores billions of years ago, scattered by supernovae, collected into molecular clouds, incorporated into our solar system during its formation. You are literally made of stardust. Stephenson 218 continues this ancient cycle. Right now, it's synthesizing heavy elements through nuclear fusion in its core and inner shells. When it explodes, those elements will scatter across light years of space. Some fraction will eventually help form new stars and planetary systems. Perhaps, billions of years from now, intelligent beings will walk on a planet containing atoms from Stephenson 2-18, looking up at their night sky and wondering about their cosmic origins. That's not mere poetic speculation. It's inevitable consequence of galactic chemical evolution. The elements Stephenson 218 produces will disperse and mix with other material. Star formation in the region will continue. Some of that enriched gas will collapse into new stars. The timeline might be long, 10 million, 100 million years, but it will happen. Meanwhile, we watch and measure and model, trying to understand these extraordinary objects before they vanish. Stephenson 218 might explode tomorrow or survive for another 100 millennia. Either way, it won't last long by cosmic standards. Its time is measured in stellar eye blinks. How many humans have gazed at the patch of sky containing Stephenson 2-18 without knowing it's there? Thousands? Millions? It's invisible to unaided vision, hidden behind layers of dust, detectable only with sensitive infrared instruments. Yet, it's one of the largest objects in the galaxy, a star so enormous that if you could somehow transport it to our solar system's center, its surface would reach beyond Jupiter's orbit. That juxtaposition, immense yet invisible, characterizes much of astronomy. The universe contains countless wonders we cannot perceive directly. Our atmosphere blocks most electromagnetic radiation. Dust obscures vast regions of the galaxy. Distance dims even the brightest objects to faint points of light. We're like people trying to understand an elephant while blindfolded, touching only small parts, inferring the whole from limited information. But we're getting better at it. Every new telescope, every improved detector, every refined analysis technique reveals more. Infrared astronomy, barely possible 50 years ago, now routinely penetrates dusty regions invisible to optical telescopes. Interferometry combines multiple telescopes to achieve angular resolution impossible for any single instrument. Adaptive optics compensates for atmospheric turbulence, delivering near-space quality images from ground-based observatories. These technological advances drive discovery. Stephenson 218 wasn't detectable with 1960s technology. Even if someone had pointed a telescope at its exact location, they'd have seen nothing interesting. Just faint infrared glow buried in background noise. Only with modern infrared arrays, sophisticated data processing, and careful analysis did this object reveal itself as extraordinary. What else remains hidden, waiting for the next technological breakthrough? How many stars even larger than Stephenson 218 exist in heavily obscured regions we haven't surveyed properly yet? The galaxy spans 100,000 light-years. We've mapped perhaps a tiny fraction thoroughly enough to detect rare objects like extreme red supergiants. Most of the galaxy remains poorly explored, especially regions near the galactic center, where dust extinction becomes severe. Future surveys will cover more territory with greater sensitivity. Automated search algorithms will sift through petabytes of data, flagging unusual objects for follow-up study. Machine learning techniques will identify patterns humans might miss. Gradually, the census of extreme stars will grow more complete. But complete certainty remains impossible. There will always be the star we couldn't detect because it's perfectly aligned behind a dark nebula, or because it exploded the day before we pointed our telescope in that direction, or because it exists in a galaxy too distant for current instruments to resolve individual stars. Astronomy constantly operates at the edge of the detectable. That's the paradox of studying rare phenomena. You need luck, being in the right place at the right time with the right equipment. Stephenson 218 could have erupted into supernova centuries ago, its light still traveling toward us. We'd observe it today, never knowing we're watching something that already happened. Or perhaps it's stable for now, quietly fusing whatever fuel remains in its core, buying itself another million years before catastrophe strikes. The cluster surrounding Stephenson 218 contains other red supergiants, though none approaching its size. Studying them collectively provides context. Are they all roughly the same age, born from the same molecular cloud? Do they show similar chemical compositions, similar mass loss rates, similar evolutionary patterns? Comparing multiple examples helps constrain theoretical models. Single objects can mislead. Maybe Stephenson 2-18 is unusual even among extreme stars, shaped by circumstances that won't repeat elsewhere. But if its siblings show family resemblances, that suggests common underlying physics rather than cosmic accidents. Spectroscopic analysis reveals what's happening in these stellar atmospheres. Absorption lines indicate which elements are present, their temperatures, their velocities. Emission lines show material being ejected, sometimes at hundreds of kilometers per second. Mass emission, natural amplification of specific wavelengths by molecules in the circumstellar envelope, provides another diagnostic tool. Stephenson 218 shows strong mass signals, indicating dense concentrations of molecules like water vapor and silicon monoxide in its surrounding gas. Water vapor around a star might sound strange, but remember, these objects aren't hot by stellar standards. Surface temperatures around 3,200 Kelvin allow molecules to survive in the outer atmosphere and surrounding envelope. That's still hot enough to vaporize any solid material instantly, but cool enough for chemical bonds to form. The environment creates a kind of stellar chemistry lab, producing complex molecules that later seed interstellar space. Silicon monoxide masers specifically tell us about dense regions where gas is being accelerated outward. The maser emission requires specific conditions: right temperature, right density, right velocity gradients. Finding these signals confirms that Stephenson 218 is actively shedding mass in structured outflows, not just leaking gas uniformly in all directions. The geometry matters for understanding how material escapes the star's gravity and what happens to it afterward. All this data gets fed into computer models attempting to simulate red supergiant evolution. You start with initial conditions: mass, composition, rotation rate. and let physics equations evolve the star forward in time. Fusion reactions in the core produce energy and new elements. Convection carries heat and material between different layers. Radiation pressure pushes against gravity. The model tracks thousands of variables simultaneously, calculating how the star changes over millions of years. Running these simulations requires significant computational resources. Modern codes use sophisticated numerical methods to solve equations that have no analytical solutions. You're tracking nuclear physics, thermodynamics, fluid dynamics, radiative transfer, and more, all coupled together in non-linear ways. Small changes in input parameters can produce dramatically different outcomes, which partly explains why estimates for Stephenson 218's properties vary so much between studies. Different research groups use different codes, different assumptions, different calibrations. One team might prioritize matching observed luminosities, accepting larger uncertainties in radius. Another team might focus on getting surface temperatures right, which then affects how they interpret infrared observations. There's no single correct model, only models that match observations better or worse, that make testable predictions, that illuminate different aspects of stellar physics. This is normal in science. Complex systems rarely yield to simple analysis. You triangulate truth from multiple perspectives, gradually narrowing the range of possibilities. Today's best estimate for Stephenson 218's radius might be revised tomorrow when someone develops a better distance measurement technique or improves atmospheric modeling. That's not failure, that's progress. Our knowledge becomes more refined, more accurate, more useful for predicting what happens next. What would it look like to observe Stephenson 218 up close? Obviously impossible with current technology, but worth imagining. From a hypothetical vantage point, a few astronomical units away, comparable to Earth's distance from the Sun, the star would dominate the sky. Not as a point of light, but as a vast reddish wall, filling your field of view no matter which direction you looked. The surface wouldn't appear uniform. Convection cells, each larger than Earth's orbit, would create mottled patterns of slightly brighter and dimmer regions. The atmosphere would be dynamic, turbulent. Material would rise in hot upwellings, cool and fall back down, creating circulation patterns driven by the star's internal energy. But unlike the Sun, where convection zones occupy a relatively thin layer, red supergiants have convection throughout much of their volume. The entire star churns and boils, mixing material from core to surface over timescales of thousands of years. From this close perspective, you'd also notice the mass loss directly. Streams and clouds of gas would be visible, illuminated by the star's light, flowing outward in complex patterns. Sometimes the flow might appear steady, sometimes gusty, responding to changes in the star's internal structure. Dust grains would form in cooler regions farther out, creating hazy veils that obscure the surface. Massive emission would produce bright spots where conditions amplify specific wavelengths. Temperature would be noticeable even at a distance. Despite the star's relatively cool surface temperature by stellar standards, the sheer size means it radiates enormous energy. Your hypothetical observation platform would need serious shielding to avoid being vaporized. The radiation isn't primarily visible light. Most of the energy emerges in infrared wavelengths, which is why infrared telescopes are essential for studying these objects from Earth. Gravity at the surface would be surprisingly weak. Despite the star's enormous mass, perhaps 25 times the Sun's, The radius is so large that surface gravity ends up lower than Earth's. Material doesn't need much velocity to escape. That's why mass loss occurs so readily. The star's gravity barely holds its outer layers. Any perturbation, pulsation, convection, radiation pressure can push material beyond the escape velocity threshold. This weak surface gravity also affects the atmosphere's structure. It extends far from the nominal surface, gradually transitioning into the surrounding envelope with no sharp boundary. Defining where the star ends and space begins becomes arbitrary. Astronomers typically use a specific optical depth threshold, the distance where the gas becomes transparent to a particular wavelength. But that's a measurement convention, not a physical surface like Earth's ground. If you could somehow survive the environment and make measurements, you'd find interesting physics. The gas pressure, density, and temperature would follow predictable relationships dictated by thermodynamics and hydrostatics. Chemical abundances would reveal the star's nuclear processing history. Isotope ratios would tell you which reactions occurred in the core and how thoroughly mixing distributed those products through the envelope. You might detect neutrinos streaming out from the core, carrying information about fusion reactions happening deep inside. Unlike photons, which take thousands of years to random walk their way from core to surface, neutrinos barely interact with matter. They escape directly, providing a real-time window into the stellar interior. Detecting them would require sensitive equipment, but they'd confirm whether the star is still burning helium, or if it's moved on to heavier elements like carbon or oxygen. Magnetic fields likely exist, but probably aren't as strong or organized as in smaller stars. The Sun has a well-defined magnetic field generated by dynamo processes in its convective zone. Red supergiants have convection throughout their volume, which should generate magnetic fields, but the details remain poorly understood. Observations suggest weaker, more chaotic fields than in main sequence stars. These fields might help shape mass loss patterns, creating the asymmetries sometimes observed in circumstellar envelopes. Returning to reality, we observe Stephenson 2.18 from 20,000 light-years away using ground-based telescopes and occasionally space-based instruments. Each observation adds data points to our understanding. Infrared photometry tracks brightness variations. Spectroscopy reveals chemical compositions and velocities. Interferometry measures angular sizes. Radio observations detect massive emission. Together, these pieces construct a coherent picture of an object we'll never visit. The star's variability complicates analysis. Like most red supergiants, Stephenson 2-18 doesn't maintain constant brightness. It pulsates, expanding and contracting with periods of hundreds or thousands of days. These pulsations aren't regular like a clock. They're quasi-periodic, with amplitude and frequency changing over time. During expansion phases, the star grows larger and cooler. During contraction, it shrinks and heats up slightly. Size estimates depend on when you observe it. This behavior isn't fully understood theoretically. Models can reproduce some pulsation characteristics, but struggle with others. The fundamental driving mechanism likely involves opacity changes in the atmosphere. As temperature varies, the gas becomes more or less transparent to radiation, which affects how efficiently energy escapes, which feeds back into the temperature and pressure, creating oscillations. But the details get complicated quickly. especially when you factor in convection, rotation, and mass loss. Some researchers suggest that irregular pulsations might trigger enhanced mass loss episodes. A particularly strong pulsation could temporarily increase the atmosphere's size and decrease its density, making it easier for radiation pressure to push material beyond escape velocity. If this happens repeatedly, the cumulative effect could strip away significant mass over relatively short timescales. Evidence for this comes from observations of circumstellar shells around some red supergiants, suggesting episodic rather than continuous mass loss. Stephenson 2-18 might be undergoing such episodes now. The high infrared excess indicates substantial dust in the surrounding envelope, consistent with recent or ongoing mass ejection. Whether this represents the star's normal state or a temporary phase remains unclear. Monitoring over years or decades would reveal trends, but funding for long-term observational programs is often difficult to secure when competing against newer, flashier projects. The broader question persists: how do stars this large form in the first place? Initial mass determines evolutionary path. Stars born with 8 solar masses or more will eventually explode as supernovae. Stars above perhaps 25 solar masses might collapse directly into black holes. But stars with initial masses of 30, 40, 50 solar masses or more face additional challenges during formation. Massive star formation happens in giant molecular clouds where gas densities are high. Gravity pulls material together, forming a protostellar core. As mass accumulates, the object heats up from gravitational compression. Eventually, temperature and pressure in the core become sufficient to ignite fusion. But for very massive stars, radiation pressure from fusion can halt further accretion before the star reaches its full potential mass. This creates a theoretical upper limit to stellar mass, somewhere around 150 to 200 solar masses for typical conditions. Stars more massive than that should blow themselves apart during formation. Yet observations occasionally reveal stars that seem to exceed this limit, suggesting either the limit is softer than theory predicts, or these objects formed through special circumstances, perhaps mergers of smaller stars, or unusually low metallicity environments where radiation pressure is less effective. Stephenson 2-18 likely started with initial mass in the 30 to 40 solar mass range, possibly higher. Over 17 million years, the cluster's estimated age, it evolved from a hot, compact main sequence star into the bloated red supergiant we observe today. The transformation required burning through its hydrogen fuel, expanding as core fusion shifted to heavier elements, shedding mass through stellar winds, all while convective mixing brought processed material to the surface. Now it exists in a precarious state, balance between fusion energy pushing outward and gravity pulling inward, slowly consuming whatever fuel remains accessible. The end comes when that balance breaks, when the core exhausts its nuclear options and collapses, triggering the supernova that will briefly outshine the entire galaxy before fading, leaving behind a neutron star or black hole. That dramatic finale raises another question. What actually triggers the supernova itself? Core collapse sounds straightforward, but the mechanism involves physics operating at extremes that still puzzle researchers. When fusion ceases, the iron core contracts rapidly under gravity. Electrons get squeezed into protons, forming neutrons and releasing neutrinos. Within a second, the core shrinks from roughly Earth's size to maybe 20 kilometers across. densities reach levels comparable to atomic nuclei, unimaginable compression that creates a neutron star. The outer layers, no longer supported, plunge inward at significant fractions of light speed. They hit the newly formed neutron core and bounce. That rebound, combined with the enormous flux of neutrinos streaming outward, blows the star apart in a Type II supernova. At least that's the simplified version taught in introductory astronomy courses. Reality proves messier. Computer simulations of core collapse supernova struggled for years to produce explosions. Early models showed in falling material simply piling onto the proto-neutron star without rebounding strongly enough to reverse the collapse. Researchers kept refining their codes, adding better neutrino physics, improving resolution, incorporating magnetic fields and rotation. Modern simulations now successfully explode, but the process teeters on a knife edge. Small changes in initial conditions, slight differences in rotation rate, core structure, or neutrino opacity can mean the difference between a successful supernova and a failed one that forms a black hole directly without much visible display. Some massive stars might experience such failed supernova, collapsing quietly into darkness. We'd never know unless we happened to be monitoring that particular star at the time, noticing it suddenly disappeared from observations. Stephenson 218 will probably explode successfully given its mass and composition, but certainty remains elusive. The supernova itself will be spectacular, briefly radiating more energy than the entire cluster combined, visible across the galaxy despite 20,000 light-years distance. For a few weeks, it might even be visible to the naked eye from Earth, appearing as a moderately bright star in Scutum before fading over months. The explosion will disperse much of the star's mass, enriching the interstellar medium with heavy elements forged during the star's lifetime and in the supernova itself. Elements heavier than iron form primarily in these explosive events, where neutron capture processes have time to build up atomic nuclei beyond what normal fusion allows. Gold, platinum, uranium, these owe their existence to supernovae and related cataclysms. The expanding debris will sweep through surrounding space, triggering shockwaves that compress nearby gas clouds, potentially inducing new star formation. The remnant at the center will be either a neutron star or a black hole, depending on how much mass falls back onto the core after the initial bounce. Neutron stars are bizarre objects in their own right, stellar corpses so dense that a teaspoon of their matter would weigh billions of tons on Earth. They can spin hundreds of times per second, generating powerful magnetic fields that channel radiation into beams, creating pulsars we detect as regular radio pulses, or they might be magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, occasionally releasing bursts of energy that briefly outshine the entire galaxy in gamma rays. If enough mass falls back, the neutron star crosses its stability limit and collapses further into a black hole, a region where gravity becomes so intense that not even light escapes. Black holes from stellar collapse typically range from a few solar masses up to perhaps 50 or 60, though recent gravitational wave detections hint at heavier ones forming through mergers. The black hole left by Stephenson 218 would likely fall in the 10 to 20 solar mass range, accounting for the mass lost through winds and the supernova ejection. Either outcome represents the final transformation, the ultimate endpoint of the stellar evolutionary sequence that began 17 million years ago, when a dense clump in a molecular cloud started collapsing under its own gravity. From protostar to main sequence star to red supergiant to supernova to neutron star or black hole. The journey spans millions of years, but the final collapse happens in seconds. That timescale contrast captures the dramatic nature of stellar evolution. Long periods of relative stability punctuated by rapid transformations. Our Sun will never experience such drama. It lacks the mass needed to become a supergiant or explode. Instead, in 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, possibly Earth too. Then it will shed its outer layers gently, forming a planetary nebula, while the core contracts into a white dwarf, a different kind of stellar remnant, supported not by fusion or neutron degeneracy pressure, but by electron degeneracy, the quantum mechanical resistance of electrons to being compressed. White dwarfs cool slowly over trillions of years, eventually fading to black dwarfs, though the universe hasn't existed long enough for any black dwarfs to form yet. They represent the future of most stars, quiet cooling rather than explosive demise. Only the massive stars, those born with 8 solar masses or more, die young and violently. They burn through their fuel quickly, shine brilliantly, and end catastrophically. Stephenson 218 exemplifies this pattern taken to an extreme. A star so massive it became enormous, so luminous it rivals small galaxies, so unstable it sheds mass continuously, and destined to explode with such force that the event will be visible across a significant fraction of the observable galaxy. The sheer scale challenges intuition. 2,000 times the Sun's radius means the volume exceeds 10 billion suns. If hollow, you could fit our entire inner solar system inside with room to spare. The surface area equals roughly 40 million times Earth's. Standing on a hypothetical planet orbiting at a safe distance, the star would span a substantial arc of the sky, glowing dull red, its limb darkening effect making the edges fade gradually into space. The view would be alien and unsettling, a bloated crimson orb dominating the heavens, slowly pulsating, occasionally ejecting clouds of gas that would glow as they caught stellar radiation. Any closer, and the tidal forces would tear planets apart. Any farther, and the light would dim too much to support conventional life. Not that life could exist near such a star anyway. The intense radiation, stellar winds, and short lifetime would preclude biological evolution. By the time multicellular life might develop, the star would already be dead. Life requires stable, long-lived stars like our Sun. Middle-aged, unremarkable yellow dwarfs that burn steadily for billions of years. Massive stars are the universe's fireworks, spectacular but brief, yet they play crucial roles in cosmic ecology. Their deaths distribute heavy elements necessary for planet formation and life. Without generations of massive stars living and dying, enriching the interstellar medium, the universe would remain mostly hydrogen and helium. No carbon for organic chemistry, no oxygen for water, no silicon for rocks, no iron for planetary cores. Earth itself is built from the ashes of dead stars, many of them likely red supergiants that exploded as supernovae billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged inside massive stars and scattered through space when they died. This connection makes stellar evolution deeply personal. We are literally made of stardust, descendants of stellar nucleosynthesis. Stephenson 218, when it eventually explodes, will contribute to future generations of planets and potentially future life forms that won't exist for billions of years. The atoms currently swirling in its envelope might one day be part of a distant world's ocean or a future being's body. That continuity, matter recycling through cosmic timescales, connects everything across space and time. How many stars like Stephenson 2-18 exist in the galaxy? Red supergiants are uncommon, but not exceptionally rare. The Milky Way probably hosts thousands at any given time, though most are too distant or obscured to detect easily. Each represents a massive star in late evolutionary stages, destined to explode within the next few million years. Some are even larger than Stephenson 2-18, though measurement uncertainties make definitive rankings difficult. Others are smaller, but still enormous by normal standards. Together, they form a population of dying giants scattered throughout the galactic disk. Their distribution isn't random. Massive stars form in clusters, born from the same molecular cloud. They tend to remain relatively close to their birthplace, though over time, gravitational interactions and galactic rotation disperse them. Stephenson 2 cluster contains multiple red supergiants, suggesting a burst of star formation 17 million years ago that produced several massive stars now reaching the end of their lives. In a few million years, they'll explode sequentially, each supernova potentially triggering more star formation in nearby clouds, seeding the next generation. This cycle has repeated countless times since the galaxy formed over 13 billion years ago. Early generations of stars were metal poor, containing only hydrogen and helium from the Big Bang. They lived and died, enriching the interstellar medium. Subsequent generations incorporated those heavy elements, allowing rocky planets and eventually life. We exist in an era where multiple generations of stellar evolution have built up substantial metallicity. Future stars will be even more metal-rich, assuming star formation continues long enough. But the universe's expansion and the gradual consumption of gas into stars and stellar remnants means star formation will eventually cease. In 1 trillion years, the last stars will be dying and the universe will enter a dark era dominated by stellar remnants. Stephenson 2-18's explosion will occur long before then, but it's part of the same grand narrative. The universe's ongoing evolution from the hot, dense state of the Big Bang toward the cold, diffuse future where stars no longer shine. That cosmological perspective contextualizes individual stars. Each one, no matter how spectacular, is a temporary structure, an eddy in the cosmic flow, existing briefly before dissolving back into the substrate. Stephenson 2-18 may be the largest star we currently know, but it's still finite and mortal. In cosmic terms, its entire lifetime, from formation to supernova, represents a mere eye blink. The universe was ancient before Stephenson 2-18 formed. It will continue for eons after its remnant cools to invisibility. This humbling scale makes astronomy both awe-inspiring and sobering. We observe these magnificent objects, calculate their properties, marvel at their extremes, but they're ultimately transient, as are we. The difference is one of degree, not kind. Humans live decades. Stars live millions or billions of years. Galaxies persist for tens of billions. But all are temporary patterns in space-time, arising from the interplay of fundamental forces, destined eventually to dissipate. Does that diminish their significance? Perhaps it enhances it. Stephenson 2-18 exists now, shining brilliantly despite its inevitable doom. We exist now, able to observe and understand it despite our brief lifespans. The fact that both are temporary doesn't make them meaningless. It makes them precious. These moments of existence, whether stellar or human, are the universe's opportunity to experience complexity, to generate structure and beauty from simple physical laws. When Stephenson 218 explodes, it will create a spectacle that, while violent, is also creative, dispersing materials that will build future worlds. That's not tragedy, that's transformation. The atoms that comprise the star won't vanish. They'll scatter, cool, mix with interstellar gas, eventually get swept into new star-forming regions, become part of new stars and planets. Some might even participate in new forms of life, if conditions allow. The cycle continues, powered by gravity, fusion, and the fundamental laws of physics, unfolding across timescales that dwarf human comprehension, but remain understandable through careful observation and mathematical reasoning. That understanding represents one of humanity's greatest achievements. A few centuries ago, stars were mysterious lights of unknown nature. Now, we can analyze their composition from hundreds or thousands of light years away, model their interiors, predict their fates. We've discovered that the largest stars are thousands of times bigger than our Sun, that they burn through their fuel rapidly, that they'll die spectacularly. We know Stephenson 218's temperature, luminosity, mass loss rate. We understand the nuclear reactions powering it, the physics governing its structure, the evolutionary path that brought it to its current state. This knowledge didn't come easily. It required generations of astronomers building better instruments, developing theoretical frameworks, testing predictions against observations. It required physicists unraveling nuclear physics, understanding quantum mechanics, solving the equations of stellar structure. It required international collaboration, sharing data and ideas across borders and decades. The result is a coherent picture of stellar evolution that explains countless observations and makes testable predictions. That picture still has gaps and uncertainties, especially regarding the most extreme objects, but it's remarkably successful for something as complex as stars. Stephenson 218 fits within this framework, though it pushes the boundaries. Its extreme size and high mass loss rate challenge models. Its variability and infrared excess suggest complex atmospheric dynamics we're still working to understand fully. But none of this contradicts our basic understanding of how massive stars evolve. It just shows that nature explores the full parameter space available, producing objects at the edge of what's possible. Studying these extremes helps refine our theories, exposing weaknesses and prompting improvements. Every anomaly is an opportunity to learn something new. That process of discovery and verification continues. New telescopes with better resolution probe deeper into obscured regions. Improved distance measurements from spacecraft like Gaia refine our estimates. Computer models grow more sophisticated, incorporating additional physics. Each advance brings sharper focus, but also reveals new complexities we hadn't anticipated. Consider the measurement challenges. Stephenson 218 sits embedded in dense dust clouds that absorb most visible light. Only infrared radiation escapes, carrying information about the star's properties. But dust complicates interpretation. It absorbs some wavelengths preferentially, distorting the spectrum. It re-radiates energy at cooler temperatures, adding infrared excess. Disentangling the star's actual emission from these effects requires careful modeling and multiple observations at different wavelengths. Distance uncertainty compounds the problem. The star lies roughly 20,000 light-years away, but that figure has substantial error bars, potentially 50% or more. When you're trying to determine a star's physical size, distance matters enormously. Brightness decreases with the square of distance, so an object twice as far is 4 times dimmer. If our distance estimate is wrong, our luminosity calculation will be wrong. And luminosity connects directly to size through the Stefan-Boltzmann law, meaning distance errors propagate through every derived property. This isn't unique to Stephenson 2-18. Most record holder candidates face similar issues. UY Scuti's size estimates have been revised significantly as better data became available. What was once thought to be 1,700 solar radii dropped to around 900 in more recent analyses using improved distance measurements from Gaia. That's still enormous, but nearly half the original estimate. Such revisions happen regularly in astronomy as techniques improve and new data arrives. Does that make the earlier measurements wrong? Not exactly. They were the best estimates possible with available information. Science progresses through refinement, not by achieving perfection on the first try. Each generation of instruments and methods improves accuracy, narrowing uncertainty ranges, revealing details previously hidden. Today's measurements will likely be revised by future observations with instruments we haven't built yet. That's expected and healthy. What remains constant is the existence of these extreme objects, pushing stellar physics to its limits. Whether Stephenson 218's radius is 2,150 or 1,800 or 2,000 solar radii doesn't fundamentally change its nature as an extraordinarily large, unstable star nearing the end of its life. The exact number matters for detailed modeling, but the broader picture stays consistent. Massive stars evolve rapidly, expand enormously, lose mass prodigiously, then explode. The specifics vary, but the overall pattern holds. That pattern reveals something fundamental about stellar physics. There are limits to how large stars can grow, set by the balance between gravity and radiation pressure. When a star's luminosity becomes high enough, radiation pressure on its outer layers can exceed gravitational binding. Material gets blown away, carrying mass from the star. This mass loss accelerates as stars become more luminous and extended, creating a natural ceiling on stellar size. Stephenson 218 appears to be testing that ceiling. Its high mass loss rate, evidenced by strong infrared excess and MESA emissions, suggests material streaming away constantly. The star is gradually destroying itself, shedding outer layers that will never collapse inward during the eventual supernova. This pre-explosion mass loss affects the final fate significantly. Less mass at core collapse means different explosion dynamics, different remnant properties, different chemical yields. Understanding these processes requires combining observations with theoretical models. We can't watch a single star complete its evolution. That takes millions of years. But we can observe many stars at different evolutionary stages, building a composite picture. Stephenson 2-18 represents one data point in that picture, an example of extreme red supergiant evolution captured at a particular moment. Other stars in the Stephenson 2 cluster provide additional data points, all at roughly the same age, but with different initial masses and therefore different evolutionary states. The cluster context matters. Stars in Stephenson 2 formed together about 17 million years ago from the same giant molecular cloud. They share similar chemical composition and age, but differ in initial mass. The most massive have already evolved into red supergiants, while less massive ones remain on the main sequence. By studying the full population, astronomers can test evolutionary models against real data. Does the predicted progression from main sequence to red supergiant to supernova match what we observe? Mostly yes, though with details requiring adjustment. Stephenson 218 itself shows features suggesting complex atmospheric dynamics. Variable stars like this undergo periodic expansions and contractions driven by instabilities in their outer layers. Material heats, expands, cools, falls back, creating pulsations with timescales of months or years. These pulsations can be violent enough to temporarily distort the star's shape and eject material episodically. The infrared excess observed around Stephenson 2-18 might result from dust condensing in these ejected shells, forming a dusty envelope around the star. Such envelopes aren't unusual for red supergiants. Many are surrounded by extensive circumstellar matter created by ongoing mass loss. This material obscures the central star, making direct observation difficult. It also creates an extended atmosphere where chemistry happens. Molecules and dust grains form in the cooler outer regions, then get swept away by stellar winds or radiation pressure. The result is a complex, dynamic environment, quite different from the relatively simple photosphere of a main sequence star. Studying this environment requires multiple techniques. Infrared imaging reveals the spatial distribution of dust. Spectroscopy identifies molecules through their characteristic absorption or emission lines. Interferometry measures angular sizes with high precision, resolving details impossible with single telescopes. Maser emissions trace specific physical conditions in the circumstellar gas. Each technique provides different information, and combining them creates a comprehensive picture. That picture shows Stephenson 218 as an active, evolving system. The star isn't static, it's constantly changing, though on timescales longer than human observation periods. Material flows outward, carrying away mass and energy. The stellar radius fluctuates as pulsations expand and contract the outer layers. Dust forms and dissipates in the surrounding envelope. All these processes interconnect, driven by the enormous energy output from fusion happening deep in the core. Which brings us back to fundamentals. Everything we observe at the surface traces back to nuclear physics in the interior. Fusion reactions generate energy, creating pressure that supports the star against collapse. But fusion rates depend on temperature and composition. As helium builds up in the core, fusion shifts to heavier elements. Carbon burning, oxygen burning, each stage proceeding faster and at higher temperatures. The star's structure adjusts continuously in response. For extremely massive stars like Stephenson 2-18, this evolution happens remarkably quickly. A star with 25 solar masses might spend only a few million years as a red supergiant before exploding. That's a blink compared to the Sun's 10 billion year lifetime. The rapid pace reflects higher core temperatures enabling faster fusion rates. More luminosity means more fuel consumption. The candle that burns twice as bright burns half as long, except here, the ratio is far more extreme. During its red supergiant phase, the star experiences repeated cycles of expansion and contraction, sometimes ejecting significant mass in the process. These episodes might create multiple shells of circumstellar material, each representing a distinct mass loss event. Observing these shells provides clues about the star's recent history and future evolution. Did it experience a particularly violent ejection recently? Are the mass loss rates increasing as the star approaches instability? The answers have implications beyond this single object. If we understand how the most massive stars lose mass, we can predict their final fates more accurately. That matters for understanding supernova rates, neutron star and black hole formation, chemical enrichment of galaxies. Massive stars are rare, but they dominate certain astronomical processes due to their extreme properties. They inject energy into their surroundings through stellar winds and supernova explosions. They create and disperse heavy elements essential for planets and life. They shape the interstellar medium, triggering new star formation while simultaneously disrupting nearby clouds. Stephenson 218 will contribute to all these processes when it explodes. The exact nature of that explosion depends on details we're still working to understand. Will it be a standard core collapse supernova, a more energetic hypernova? Could it collapse directly to a black hole without a bright explosion? The answers depend on the remaining core mass, rotation rate, and magnetic field strength, quantities difficult to measure directly. What we can measure is the current state. The star's luminosity, temperature, mass loss rate, variability characteristics. These observables constrain models of the interior structure and evolutionary state. They tell us the star has progressed well beyond hydrogen burning, likely fusing heavier elements in its core now. They suggest instabilities that will intensify as fusion progresses through increasingly unstable nuclear regimes. They point toward an endpoint approaching within the next few million years, possibly sooner. That endpoint represents a transition from one type of astronomical object to another. The star will cease being a star in any conventional sense. Its core will collapse in seconds, releasing more energy than the sun will emit in its entire lifetime. The outer layers will be blown away, creating an expanding remnant that will remain visible for tens of thousands of years. At the center, either a neutron star or black hole will form, depending on how much mass falls back onto the collapsing core. Either outcome represents an extreme physical regime. Neutron stars pack more than a solar mass into a sphere only kilometers across, creating densities comparable to atomic nuclei. Black holes take this further, compressing matter to infinite density according to general relativity, creating space-time curvature so extreme that not even light escapes. Both represent the ultimate fate of matter pushed to gravitational collapse, preserved only by exotic physics that barely functions under such conditions. Stephenson 2-18's ultimate remnant type remains uncertain. It depends on processes happening now in the invisible core, processes we infer from surface observations and theoretical models. But regardless of details, the star exemplifies a fundamental cosmic cycle. Matter assembled into a massive star. Fusion converted light elements into heavy ones while releasing energy. That energy supported the star temporarily against gravity's inexorable pull. Eventually, fuel exhaustion allows collapse, triggering an explosion that disperses processed material back into space. The cycle completes, ready to begin again when that dispersed material collapses into new stars. This cycle has operated for billions of years, gradually enriching the universe with heavy elements. the first stars contained only hydrogen and helium from the Big Bang. When they exploded, they seeded their surroundings with carbon, oxygen, silicon, iron, elements forged in their cores and during the supernova itself. Subsequent generations of stars incorporated these elements, creating even more complex chemistry. By now, after countless stellar generations, the interstellar medium contains a full periodic table of elements, all created through nuclear fusion and supernova nucleosynthesis. Stephenson 218 participates in this ongoing process. It's creating elements now through fusion in its core. When it explodes, it will scatter those elements across light years of space. Some will eventually become part of new stars, new planets, possibly new forms of life. The atoms comprising your body originated in similar processes billions of years ago, in stars whose names we'll never know. You're made of stellar debris, recycled matter from ancient supernovae, temporarily organized into a conscious being capable of contemplating its own origins. That's perhaps the most profound connection between human existence and extreme stars like Stephenson 218. We're not separate from these cosmic processes, we're products of them. Every element heavier than helium in your body came from a star. The calcium in your bones, the iron in your blood, the carbon forming your cells, all forged in stellar cores or supernova explosions. We are quite literally made of star stuff, as Carl Sagan memorably observed. Understanding this connection transforms how we view both ourselves and the universe. We're not isolated observers watching distant phenomena unrelated to our existence. We're participants in cosmic evolution, temporary arrangements of matter that arose because earlier stars lived and died, creating the chemical complexity necessary for life. Stephenson 2-18 represents one link in that chain, a current example of processes that have operated throughout cosmic history. When this star explodes, it will create new elements and disperse them widely. Those elements might someday participate in new planetary systems, possibly hosting their own forms of life. Those hypothetical future beings might look up at their night sky and observe even larger stars, perhaps wondering about their own cosmic origins, just as we do. The cycle continues. Consciousness emerging repeatedly from matter, organized by physical laws, acting over vast timescales. This perspective shift changes everything about how we observe distant stars. When you look at Stephenson 218, you're not viewing an isolated object. You're witnessing a moment in an eternal process that connects past, present, and future across cosmic timescales. The star exists now in a specific evolutionary state, but that state resulted from conditions set billions of years earlier, when the galaxy was younger and different. The materials forming Stephenson 218 came from previous stellar generations. Those earlier stars created heavy elements through fusion, then dispersed them via supernovae. Gas clouds enriched with these elements eventually collapsed under gravity, forming new stars including the Stephenson 2 cluster. This recycling process has operated continuously since the first stars formed roughly 13 billion years ago. Each generation adds complexity to the cosmic chemical inventory. First-generation stars contained only primordial hydrogen and helium. They couldn't form planets because rocky worlds require heavier elements. When these population 3 stars exploded, they seeded space with carbon, oxygen, magnesium, silicon, iron. Second-generation stars incorporated these elements, creating even more through their own fusion processes. By now, after countless cycles, interstellar gas contains every naturally occurring element in the periodic table. Stephenson 218 formed from such enriched material, though its exact composition remains somewhat uncertain due to observational limitations. The enrichment process operates at different rates in different galactic regions. The Milky Way's central regions experience more star formation historically, leading to higher metal content in stars forming there today. Stephenson 218, located roughly 20,000 light-years from Earth near the galactic center, formed in a relatively enriched environment. This metallicity influences stellar evolution in subtle ways, affecting opacity in stellar atmospheres, wind-driven mass loss rates, and internal convection patterns. Higher metallicity generally promotes greater mass loss, which might partially explain why Stephenson 218 sheds material so rapidly despite its young age. Understanding this star requires considering multiple interacting factors simultaneously. Surface temperature determines photon wavelengths emitted. Luminosity indicates total energy output. Mass loss rate affects long-term evolution. Internal structure governs stability. Each factor connects to others through physics. Higher luminosity drives stronger radiation pressure, increasing mass loss. Greater mass loss reduces total stellar mass, affecting gravitational compression in the core. Changed core conditions alter fusion rates, modifying energy generation. It's a complex system where changing one parameter cascades through the entire structure. Astronomers construct computer models attempting to capture these interactions mathematically. Modern stellar evolution codes incorporate detailed physics, including nuclear reaction networks, radiation transport, convection modeling, mass loss prescriptions, and rotation effects. Researchers input initial conditions, mass composition, rotation rate, then let equations predict how the star evolves over millions of years. These models successfully reproduce many observed stellar properties, lending confidence to predictions about stars like Stephenson 2-18. Yet models contain uncertainties. Some physical processes remain incompletely understood, requiring approximations. Convection, the transport of energy via gas circulation, follows complex turbulent flows difficult to model precisely. Mass loss mechanisms, especially for extreme stars like hypergiants, involve intricate physics that current theories capture only approximately. Small uncertainties in these processes compound over evolutionary timescales, creating larger uncertainties in long-term predictions. This explains why astronomers can't definitively state whether Stephenson 2-18 will explode in 10,000 years or 100,000 years. The star's current state seems clear: massive, luminous, evolved, unstable. Its eventual fate seems inevitable: supernova explosion, probably leaving a black hole remnant. But the precise timeline depends on details like current core mass, ongoing mass loss rates, and internal mixing processes, all of which carry significant uncertainties. Observational limitations compound these theoretical uncertainties, making precise predictions impossible with current data. Future observations might narrow these uncertainties. Next-generation telescopes with improved infrared capabilities could penetrate the dust surrounding Stephenson 2-18 more effectively, revealing surface details currently obscured. Interferometry techniques continue advancing, potentially enabling direct measurement of the star's diameter with better precision. Long-term monitoring programs, tracking brightness variations and spectral changes, could constrain models by providing detailed evolutionary data. Each observational improvement refines our understanding incrementally. Meanwhile, theoretical work continues advancing. Improved computational power enables more sophisticated simulations, incorporating finer physical detail. Laboratory experiments and quantum calculations provide better nuclear reaction rates for stellar conditions. Observations of other massive stars in various evolutionary stages inform general understanding applicable to Stephenson 2-18. Gradually, piece by piece, the picture becomes clearer, even if complete certainty remains elusive. This ongoing scientific process mirrors how knowledge advances generally. Initial observations reveal phenomena demanding explanation. Preliminary theories emerge, making testable predictions. Further observations refine or contradict those predictions. Theories adapt, becoming more sophisticated and accurate. The cycle repeats indefinitely, each iteration bringing deeper understanding without ever reaching final complete knowledge. Stephenson 2-18 exemplifies this process perfectly. We know vastly more about it now than when first catalogued, yet fundamental questions persist. What makes this particular star scientifically valuable? Its extreme nature pushes stellar physics to boundary conditions. Normal stars follow well-understood evolutionary paths. Extreme stars test whether our theories work in regimes far from typical conditions. When models successfully predict hypergiant properties, that validates the underlying physics powerfully. When observations disagree with predictions, that reveals gaps in current understanding, pointing toward new physics requiring discovery. Stephenson 2-18 also provides a nearby example, cosmically speaking, of physical processes occurring throughout the universe. Similar massive stars exist in distant galaxies, millions or billions of light years away. We can't study those stars in detail due to their remoteness. But by thoroughly understanding Stephenson 2-18 and other nearby massive stars, we develop principles applicable universally. This local knowledge becomes a foundation for understanding stellar populations across cosmic distances and times. The star's connection to broader astrophysical questions extends further. Massive star explosions influence galactic chemical evolution, as discussed earlier. They also affect star formation rates in their neighborhoods. Supernova shockwaves compress nearby gas clouds, potentially triggering new star formation. Simultaneously, those shockwaves disperse and heat gas, potentially suppressing star formation in other regions. The balance between these effects shapes galactic structure and evolution over billions of years. Additionally, supernova from stars like Stephenson 2-18 might produce gravitational wave signals detectable by current or future instruments. If the core collapse proceeds asymmetrically, it generates gravitational radiation, ripples in space-time itself, propagating outward at light speed. Current gravitational wave detectors have observed signals from merging black holes and neutron stars. A nearby supernova might produce detectable signals from core collapse, providing unprecedented data about processes occurring deep inside the exploding star. Such observations would constitute entirely new ways of studying stellar deaths. Light tells us about surface and atmospheric conditions. Neutrinos, if detected, provide information about core nuclear processes. Gravitational waves would reveal information about mass motions and asymmetries during collapse itself. Combining multiple observation types creates a comprehensive picture impossible to obtain from any single method alone. This multi-messenger astronomy represents the frontier of astrophysical research. The field has moved beyond simply observing light across various wavelengths. Now we detect particles, neutrinos, cosmic rays, and gravitational waves, all carrying complementary information about cosmic events. Future supernova observations, potentially including one from Stephenson, 2-18 if it explodes soon enough, will exploit all available channels simultaneously, revolutionizing our understanding of stellar deaths. The timeline remains uncertain, though. Soon, in astronomical terms, might mean thousands of years. From a human perspective, Stephenson 218 could maintain its current state for many generations before finally collapsing. Or it might explode tomorrow. The uncertainty frustrates efforts to predict specific events, but underscores how stellar evolution timescales vastly exceed human ones. We observe snapshots of processes unfolding over millions of years, making real-time evolution invisible except for the most rapid changes. This temporal disconnect between human and stellar timescales creates interesting challenges for astronomy. We can't watch individual stars evolve from birth to death. Instead, we observe many stars at different evolutionary stages, then construct theories connecting those snapshots into coherent evolutionary sequences. It's like trying to understand human aging by looking at photographs of different people at various ages, without ever watching anyone actually age. The approach works remarkably well, validated by consistency across many observations, but it lacks the certainty of direct longitudinal observation. Stephenson 2-18 will eventually provide one data point in that evolutionary sequence. When it explodes, astronomers worldwide will immediately observe the event across all available wavelengths and channels. That observation will test predictions about massive star deaths, supernova mechanisms, nucleosynthesis, remnant formation, and galactic feedback. A single well-observed supernova provides invaluable data constraining multiple theoretical areas simultaneously. Until then, the star continues its slow march toward instability. Fusion proceeds in the core, creating ever heavier elements. The outer envelope expands and contracts according to internal dynamics we only partially understand. Mass streams away steadily, carrying material back into interstellar space. And somewhere, hidden deep within, a growing iron core accumulates inexorably toward the critical mass where collapse becomes inevitable. That moment approaches, whether in years or millennia we cannot say. When collapse finally occurs, the event will be spectacular, even at 20,000 light-years distance. For weeks or months, the supernova might outshine the entire Milky Way, becoming potentially visible in daylight, depending on exact circumstances. The explosion will create a nebula visible for thousands of years afterward, possibly rivaling famous remnants like the Crab Nebula in complexity and beauty. And at the center, a black hole will remain, forever marking where once the largest known star existed. That future black hole will itself become an object of study. Its mass will encode information about the progenitor star's properties. Its spin will reveal details about angular momentum transfer during collapse. If it receives a velocity kick from asymmetric explosion, its motion through space will tell us about explosion dynamics. Even after the visible supernova fades, the remnant continues providing scientific value indefinitely. This represents the ultimate legacy of Stephenson 218. long after human civilization potentially ends, long after Earth itself becomes uninhabitable billions of years hence, when our sun expands into a red giant, the black hole created by Stephenson 218's collapse will persist. It will orbit the galaxy eternally, occasionally encountering other objects, slowly evaporating via Hawking radiation over timescales that make the current age of the universe seem infinitesimal. The star's existence, however brief on cosmic scales, leaves a permanent mark on space-time itself. Perhaps that's the deepest lesson from studying extreme stars. They demonstrate how temporary structures can emerge from chaos, persist briefly, then dissolve back into the cosmos while leaving permanent traces. Stephenson 218 assembled from gas clouds that once belonged to other stars. It will disperse back into space, its material eventually forming new stars, planets, possibly life. But the black hole remains, and the heavy elements created persist indefinitely, incorporated into later cosmic structures. You participate in the same process. The atoms comprising your body came from stellar deaths billions of years ago. They've cycled through various forms: gas, dust, rock, biological molecules, before temporarily assembling into you. Eventually, they'll disperse again, recycling into new forms over timescales beyond imagining. The universe wastes nothing. Every atom gets reused endlessly, creating structures of ever-increasing complexity as cosmic evolution proceeds. Stephenson 2-18 represents one grand chapter in that eternal story, a chapter now approaching its dramatic conclusion before the cycle begins anew. Looking at Stephenson 2-18 from 20,000 light-years away, we're witnessing something that shouldn't exist according to our simplest models, yet clearly does. A star so massive, so extended, so unstable that it challenges every assumption about stellar limits. And that's exactly why it matters. The measurement uncertainties remain frustrating. Is the radius precisely 2,150 solar radii, or closer to 1,800? Different studies yield different answers depending on assumptions about distance, temperature, dust composition. Future observations with better instruments will refine these numbers, possibly crowning a different champion. NML Cygni might reclaim the title. Some undiscovered giant lurking in a heavily obscured region might surpass them all. But here's what the debate over exact measurements misses. The existence of these objects fundamentally matters more than their precise ranking. Whether Stephenson 218 is the absolute largest, or merely among the largest, doesn't change its significance. It represents stellar evolution pushed to extremes we're still learning to understand. It demonstrates that nature explores every possibility physics allows, creating structures at the edge of stability. These extreme stars serve as laboratories testing our theories under conditions impossible to replicate anywhere else. The temperatures, pressures, and densities in Stephenson 218's interior exceed anything achievable in terrestrial experiments. The mass loss rates, luminosities, and evolutionary timescales challenge our models in ways normal stars don't. Every observation adds constraints to theory. Every refined measurement narrows uncertainties. The star will explode eventually, maybe in 1,000 years, maybe in 100,000. The timeline remains uncertain, but the outcome seems inevitable. When collapse finally occurs, the supernova will briefly outshine billions of normal stars, visible across much of the galaxy despite the intervening dust. Astronomers will observe it with instruments far more sophisticated than those available today, capturing data that current researchers can only dream about. That observation will answer questions we haven't yet learned to ask. Until then, Stephenson 218 continues existing in its precarious state, fusing heavy elements in its core, shedding mass through powerful winds, pulsating according to internal dynamics we're still working to understand. It's simultaneously creating and destroying itself, building heavy elements through fusion while stripping away its outer layers through mass loss. The competition between these processes determines how much longer the star persists and what kind of remnant it ultimately leaves behind. The broader context matters more than any individual object. Stephenson 2-18 exists within a cluster of red supergiants, all roughly the same age, all approaching the ends of their brief lives. Within the next few million years, that cluster will experience multiple supernovae as its most massive members explode sequentially. Those explosions will enrich the surrounding interstellar medium with heavy elements, while simultaneously triggering new star formation through shock compression of nearby gas clouds. This cycle has operated since the first stars formed over 13 billion years ago. Each generation creates heavy elements through fusion and distributes them via supernovae. Subsequent generations incorporate those elements, enabling progressively more complex chemistry. Rocky planets became possible only after multiple stellar generations had enriched the interstellar medium with silicon, iron, magnesium. Life emerged only after billions of years of chemical enrichment provided the necessary elements: carbon, nitrogen, oxygen, phosphorus. You exist because stars like Stephenson 218 lived and died billions of years ago, creating the elements now comprising your body. The calcium in your bones came from stellar nucleosynthesis. The iron in your blood was forged in some ancient supernova. The oxygen you're breathing right now was created through fusion in a massive star's core, before being scattered by its explosive death. This connection transforms how we view both ourselves and the cosmos. We're not separate observers studying distant objects unrelated to our existence. We're participants in cosmic evolution, temporary arrangements of stellar debris, organized into conscious beings capable of understanding our own origins. The atoms making up your body have cycled through multiple stars over billions of years. They've existed as interstellar gas, as parts of ancient planets, as biological molecules in organisms that lived and died long before humans evolved. Stephenson 218 continues this process right now. It's creating elements through fusion that will eventually become part of future stars, planets, possibly future life forms. When it explodes, those newly created elements will scatter across light years of space, mixing with other material, eventually participating in new cosmic structures. The cycle never ends. Matter continuously recycles, creating increasingly complex arrangements as physical laws operate over vast timescales. The star's extreme properties reveal something fundamental about how the universe works. Physics allows certain maximum sizes for stars based on the balance between gravity pulling inward and radiation pressure pushing outward. Stephenson 2-18 appears to be testing that limit, existing in an unstable state where any perturbation might trigger catastrophic mass loss. The high infrared excess and strong MESA emissions indicate material streaming away constantly, suggesting the star is gradually destroying itself before the final collapse. Understanding these limits matters for cosmology. The first stars in the universe might have been even more massive than anything existing today because they formed from pristine hydrogen and helium without heavy elements to facilitate cooling and fragmentation. Those hypothetical population 3 stars might have reached several hundred solar masses before exploding as pair instability supernovae. Events so energetic they completely destroy the star without leaving a remnant. We've never observed such explosions directly, but theory predicts they occurred in the early universe. Stephenson 2.18 helps us understand whether such extreme stars can exist by showing us what happens at the upper limits of stellar mass in our current epoch. If stars this size barely survive before tearing themselves apart through mass loss, that constrains how massive the first stars could have been. Each observation of extreme objects today informs our understanding of cosmic history. The quest to find the largest star will continue. New surveys will cover more of the galaxy with better sensitivity. Improved distance measurements will refine size estimates. Advanced modeling techniques will better account for dust, variability, and complex atmospheric effects. The title of largest known star will likely change hands multiple times as measurements improve and new candidates emerge from obscured regions. But that competition, while interesting, somewhat misses the point. These objects collectively reveal how stellar evolution works at extremes. They show us what happens when gravity, fusion, and radiation pressure compete in stars far more massive than our Sun. They demonstrate the chemical enrichment process that made planets and life possible. They provide natural laboratories where matter behaves under conditions we can never recreate artificially. Stephenson 2-18 represents one example among many, a particularly large example, possibly the largest currently known, but ultimately one member of a population of extreme stars scattered throughout the galaxy. Each contributes to our understanding. Each adds constraints to theoretical models. Each enriches the interstellar medium when it dies, seeding future star formation with heavy elements. The star's existence also reminds us how much remains unknown. Despite centuries of astronomical progress, we still can't precisely predict when individual stars will explode or exactly what processes trigger core collapse. We don't fully understand convection in massive stellar envelopes or what determines mass loss rates. We can't definitively say whether a given supergiant will leave behind a neutron star or black hole. These uncertainties don't represent failures of science. They reflect the genuine complexity of nature and the difficulty of studying objects at cosmic distances. Every answered question reveals new questions we hadn't known to ask. Every refined measurement exposes new puzzles requiring explanation. The process of discovery continues indefinitely, each generation building on previous work, while recognizing how much remains mysterious. Future astronomers will study Stephenson 2-18 with instruments we haven't invented yet, applying theoretical frameworks we haven't developed, asking questions we haven't conceived. They'll refine our measurements, correct our errors, and probably smile at how primitive our current understanding seems. That's how science progresses, not through achieving final complete truth, but through continuous refinement approaching closer to reality without ever fully arriving. And eventually, perhaps thousands of years from now, perhaps sooner, Stephenson 2.18 will explode. Those future astronomers will observe the supernova with technologies far beyond current capabilities. Capturing data, that will revolutionize understanding of stellar deaths. They'll detect neutrinos from the core collapse, gravitational waves from asymmetric mass motions, electromagnetic radiation across all wavelengths from radio to gamma rays. They'll watch in real time as shock waves tear through the stellar envelope, as heavy elements get synthesized in the explosion's heat, as a black hole forms at the center. The observation will answer questions while raising new ones, as all major discoveries do. But it will also represent a transition, the end of Stephenson 218 as a star, and its transformation into a supernova remnant. Then eventually just a black hole orbiting silently through the galaxy for eons to come. Until that moment arrives, the star continues its existence in our night sky, invisible to unaided vision, but blazing brilliantly in infrared wavelengths for those with instruments to detect it. It shines with the power of hundreds of thousands of suns, illuminating nothing but empty space around it, slowly dying while simultaneously creating the heavy elements that make complexity possible. Every second, fusion reactions in its core convert mass to energy according to Einstein's equation. Every second, stellar winds carry material away at hundreds of kilometers per second. Every second, the star inches closer to the moment when fusion can no longer support the weight of its own mass, and collapse becomes inevitable. That moment will come. The timeline remains uncertain, but the physics seems clear. And when it happens, when Stephenson 218 finally reaches the end of its brief, spectacular existence, it will create one of the most energetic events possible in the universe. A core collapse supernova that will briefly rival the combined light of 100 billion stars. But even in death, the star's atoms won't vanish. They'll scatter, disperse, mix with interstellar material, eventually collapse again under gravity to form new structures. The cycle continues, powered by the same fundamental forces that have shaped cosmic evolution since the Big Bang. Matter assembles, fuses, disperses, reassembles in endless repetition. Stars are born, live briefly or long depending on their mass, then die, sometimes quietly, sometimes explosively, always contributing their processed material back to the cosmos. This is the story of Stephenson 218, the largest star we currently know. A story that began 17 million years ago when a dense clump in a molecular cloud started collapsing. A story that will end in spectacular explosion within the next few million years at most. A story that's simultaneously unique and universal. One star among hundreds of billions in our galaxy alone, yet also an extreme example revealing fundamental truths about how stars work and how the universe evolves. The atoms comprising that star will persist long after the explosion fades. They'll become part of new stars, new planets, possibly new forms of life billions of years hence. Those hypothetical future beings might look up at their sky and wonder about their origins just as we do, never knowing that some of the atoms in their bodies came from a star called Stephenson 218 that exploded eons before their existence. And in that continuity, that endless recycling of matter through cosmic time, we find perhaps the deepest meaning. Nothing is permanent, but nothing is truly lost either. Everything changes form continuously while the underlying substance persists. Stars are temporary structures, as are planets, as are living beings. But the atoms endure, cycling through configurations of ever-increasing complexity as the universe's story unfolds. Right now, In this moment, Stephenson 2-18 exists somewhere in the constellation Scutum, 20,000 light-years away, shining with almost incomprehensible power, slowly destroying itself while creating elements that will outlast its existence by billions of years. It's simultaneously one of the most extreme objects in the galaxy and a natural consequence of physical laws operating under particular conditions. It's both extraordinary and inevitable, a product of stellar evolution following its course to the extremes that physics allows.